Hey guys, welcome back to the channel. We're all aware of computer chips, right? These are small integrated circuits that form the most important parts of our computer function. They can perform mathematical calculations and take decisions, making these chips the brain of the computer. But has it ever crossed your mind how this chip is constructed and what makes it so efficient? We'll find the answers to these questions in this video. The chips that we find in our computer are made up of millions of tiny components called transistors. In a CPU, many chips are placed together to form the memory of the computer. So now that we know chips are made of a transistor, what is a transistor made of then? Now, when I say a transistor, this is what will be coming to your mind. These are through-hole transistors. They are commonly available in any electronics shop, or you would have seen it in the electronics lab in your college. These modern compact transistors have a long history behind them that starts in 1904 with the invention of vacuum tubes. Vacuum tubes were invented by John Ambrose Fleming. It consisted of a vacuum glass envelope that had a cathode filament, a grid, and an anode plate. When voltage was applied across the grid, it led the cathode to heat up and generate electrons. These electrons then passed through the grid. As this setup did not have any medium inside, the electrons had very little resistance and were attracted to the positively charged anode, completing the circuit. This led to the flow of a current. This current could be manipulated. If instead of a positive voltage, a negative voltage was to be applied, then the electrons would be repelled by the anode and the circuit would not be switched on. This is the principle used behind the transistor behaving as a switch. Now, even though the setup was capable of performing large calculations in a shorter duration, they had their disadvantages. They required a large amount of electricity to function. They were bulky and slow. Then semiconductors came into the picture. Semiconductors are materials that have their conductivity between an insulator and a conductor. That is, it functioned only under specific conditions. These semiconductors were silicon metals that had the size of a grain of sand. The valence shell, that is the outermost shell of the silicon atoms, had 4 electrons. If you remember from what was taught in school, the valence shell requires 8 electrons in its outermost shell to complete its configuration. Thus, the silicon atom requires 4 more electrons to complete its configuration. To do this, dopants or impurities were introduced into the metal. These dopants were of 2 types and thus gave us 2 different types of semiconductors. First, the N-type semiconductor, which has excess electrons or negative ions, and the second, the P-type semiconductor, which has excess holes or positive ions. Now, the first type of dopant were metals that had 5 electrons in its valence shell. Example, phosphorus. Out of these 5 electrons, 4 form a covalent bond with the silicon atoms and 1 atom roams around freely in the structure. This free electron made it an N-type semiconductor having an extra number of electrons. The second type of dopant included a metal that has 3 electrons in its outermost shell. Example, boron. Now, boron having 3 electrons in its outermost shell will try to take 1 electron from its neighboring silicon atom. This creates a hole in the silicon atom which increases the number of mobile charges. This creates a P-type semiconductor. Now, these semiconductors were arranged in 2 fashions to form 2 types of transistors, NPN and PNP transistors. Each of these types had 3 terminals: the emitter, the base, and the collector. The term transistor originates from 2 words: transfer and resistance. A transistor is a device that changes resistance from high to low for them to function, and because of this property, they also amplify any input signals. Depending on the type of transistor, the emitter and collector changed roles accordingly. The base, however, remained the gate to control supply of electricity. Before understanding an NPN and PNP transistor, let us learn a very important term: depletion layer. The P-type semiconductor is filled with holes and the N-type semiconductor is filled with electrons. When these 2 semiconductors are brought together, the electrons from the N region develop a tendency to migrate towards the holes at the P region, leaving a positive ion behind. Because of this combination, a negative ion is created at the P region. This creates a region called the depletion layer. The depletion layer inhibits any further electron transfer unless a forward bias is applied. That is, the P-type is connected to the positive terminal and the N-type is connected to the negative terminal. In an NPN transistor, electrons are the majority carriers. Here the flow of charge is from the collector to the emitter. Similar to this, a PNP structure is also prevalent. Here, an N-type structure is sandwiched between the P-type structures. The majority of carriers here are holes. Here the current flows in the opposite direction. The emitter emits holes which are collected by the collector. They are used in push buttons for calculators, magnetic locks, etc. Transistors are widely used as switches and amplifiers. As switches, we can find their application in ICs for logic gates and NOT and OR. They are used as amplifiers in optical fiber communication and radio signals to have an output with high signal intensity. Transistors are used in our computers and laptops, where they are manufactured carefully in small sizes. A laptop today easily consists of 2 billion transistors. The computers we had earlier could perform an operation in 4 hours. Today, the same operation by modern computers is done in 4 seconds. Now, isn't that great? The transistors thus today are compact in size and faster in operation. Well, that's all about transistors that have shaped our modern world. We'll see you in the next video. Until then, bye.